Hello, we are Team 2, and this is our oral argumentative exposition for the report 4 or final report for the animation of a car on a Formula 1 track. Our team members are Jimena Patricia, García Magdaleno, Diego López Garza, Mauricio Rafael Castillo, Arturo Cabrera Gómez, and Emiliano Cruz Andes.
Formula One represents the absolute pinnacle of motorsports engineering. These are the fastest, most technologically advanced racing cars in the world. F1 combines cutting-edge aerodynamics, materials science, and precision engineering. Each car is essentially a ground effect vehicle that can generate more downforce than its own weight at high speeds.
Okay. For our problem statement, first we had to design a safe curve for the track. For this, we help us by designing a third grade polynomial equation. Then we calculate the curvature using the second and the first derivative of the polynomial. Then we calculate the arc length, and using physics we help us to analyze the forces, the friction, and the centripetal acceleration of our car during the track. Also, we need to place the terraces or the bleacher zones where the viewers were going to be, and this is really important because basically we had to analyze the best way where our spectators could see or view the race safely. Then we have to calculate the mechanical energy loss transforming into heat. For this, we base our simulation on the work energy theorem, and also we calculate the heat by using the equation mu times mass times gravity times distance. Then we had to simulate the car when it stayed on the curve and also when it skidded by comparing the maximum velocity with the centripetal force, also the maximum velocity at each point that didn't exceed it, so the car didn't skid.
Before we started, we had to select a location, which was the F1 Monza circuit in Italy. Then we were given two control points, which are the first two you see on the screen, and then we had to make two other points for the program to work. And afterwards, we had to give it other inputs such as the banking angle, which you can see on the screen, the static and kinetic friction, the track width, the car mass, and the acceleration of gravity.
For the mathematical modeling of the curve, we used a third order polynomial, which of course needed 4 control points. And we had to make a matrix multiplication for this, which was A times the point A and point B, point C, and point D to the power of T. And we solved this using MATLAB with a MATLAB function called coefficient equals A divided by y, which y was the matrix. And when we graph this, it shows a smooth curve throughout all the control points with equally spaced values.
We use this formula to calculate the length of the racetrack. What does this formula does? The idea is to see the curve as many small segments of straight lines, and each small segment has a specific length. So with this length, what we can do is basically sum up with these tiny segments close to zero, and then we can know the length of the curve by using integrals and their derivatives.
For the skidding line equation, we basically calculate the tangent line with the formula given by the polynomial equation that says that if first of all if the frictional force is no longer able to provide the requirement centripetal force, The result is that the tires lose grip and the vehicle can no longer follow the curvature path of the racetrack. Instead, it follows the tangent line, which is given by this. If y is our equation, then we have to calculate the derivative of y, and then by that we get the slope, and with the slope we calculate the slope point equation, and that's how we calculate the tangent line, which is the line that our car is going to follow if it skids.
We place the bleachers where the risk is the highest, in the skid zone where the R is bigger than 50. The 40-meter setback is our critical runoff distance to protect spectators from skidding cars. The position, we put it outside of the curb and away from the inward impact so the car's inertia is away from the stand. And the orientation is parallel to the tangent to prevent a direct collision.
Now moving on to the force analysis, we see the forces that keep the car on the track. For the vertical forces, we got the weight and the normal force, and for the lateral forces, we got the banking, which was 5 degrees, the kinetic friction, which was 0.8, the static friction, which was 1.7, and the centripetal force, which was the force required for the car to not skid.
So to determine the maximum speed in our code, we first need the curvature, which we have already gotten. Then with this curvature, we can get every possible value of the radius at a specific point, and we choose to get the smallest possible value of radius, which has a threshold of 50. And with this, we just calculate it with this formula for the maximum velocity, and it will give us the maximum safe speed.
Now, let's go with the energy analysis. In this slide, we analyze what happens to the car's energy because of the friction. Friction always removes energy from the car when it turns into heat. The way we calculate it is with this formula that is shown here, and we compare two situations. In the first case, the cars stay in the curves and only travels through the curve length, so the energy lost is equal to the coefficient of friction plus mass times distance. Everything is multiplied. And then this means we are multiplying the friction force by the distance, and this is converting into the energy that is lost in the system. And in the case 2, the car enters the curve 2, and friction can supply enough force to keep the car in this curve to the centripetal force, and then the tire loses grip and the car slides and goes through the tangent line that is shown in the racetrack. This means the car loses more energy because it slides out, and it also travels more distance. So in this case, the car lost more energy.
For the simulation description, we use MATLAB for this project, as well as the track was defined by a cubic polynomial curve, and we had as legend the track, the center line, the skid zone, which is marked with yellow in our track, the critical tangent, which will be the line that the car will follow if it skids, then the bleacher zones, which are in blue. Then with red star we mark the minimum radius point, and the control points are in green, as well as we display the maximum velocity, which in our case was 95 kilometers per hour, and the energy lost.
In this simulation case, the car enters the curve at a safe speed, so the friction is able to provide the centripetal force needed to follow the path. The vehicle remains fully on the track. There is no skidding or loss of control, and only a small amount of energy is lost due to normal rolling friction.
So for the part where the car will skid off the track, we first need the condition where the speed is exceeding the maximum safe speed, and then the centripetal force has to be above the static friction force available for the tires. And then at this point, the car will start going off the track in a tangent line with the curve, and the tangent line starts at the point where the car starts to skid. The only force acting on it at this point is the loss of the kinetic friction. The kinetic friction, which makes it lose the kinetic energy through friction. and then the program will eventually display the distance at which it stopped, and the energy it lost, and the time that it took it to stop.
After all the phases in this project and all the calculations, we've acquired many different results, and we've come away with some conclusions. We found that when an F1 car stays on track, it loses no energy, but whenever it skids, the kinetic friction goes along the direction of motion, converting the car's kinetic energy into heat. Um, this causes it to lose a significant amount of mechanical energy, which is a good thing as the friction slows down the car and prevents possible accidents.
To conclude, this project allowed us to combine mathematics, physics, and programming to understand how a race car behaves on a curved track. The cubic polynomial gave us a smooth and realistic track shape, the Arling formula provided us a real distance traveled, and the curvature analysis helped us determine the maximum safe speed. This simulation showed when the car respects this speed, it stays on the track, but if it exceeds the limit, friction can no longer provide the centripetal force and the car will skid out of the tangent, just like in real life. Our energy results reinforced controlled driving minimizes energy loss, while control dramatically increases frictional energy dissipation due to sliding. And overall, this project demonstrates how mathematical modeling can accurately predict physics behavior and how even simple models can reveal critical relationships between speed, friction, and safety on a racetrack.
For the limitations and improvements of our simulation, we analyze and discuss and conclude that we could improve various limitations, as the one that is that the air drag wasn't taken into consideration in our simulation, as well as the velocity as a constant. We think that we could improve and get a more advanced simulation if we take into consideration the multiple values such as air drag, the aerodynamics of the car, and the variability of the values we use as constants in our simulation. Also, we think that could be interesting to have a longer track.
Some of the tools we used for this report and our work throughout it was MATLAB for the code, GeoGebra so we could use the functions to verify, Paint for editing, Google Maps so we could track the Monza circuit, and Google Earth so we could measure out the distance.
For the class notes we used for this project, we utilized the notes we took in physics class and also in the presentation of how to make a third grade polynomial equation. Now on to the next slide.
For our website references, these are some of our sources we use for the car weight, for the research of a real Formula One track, and some of the usual values for banking. Thank you for your
Thank you for your
attention.
attention.
This was Team 2.